Hello, good morning, my dear friends and students. Today we are discussing about design of two-way slab. First of all, I will explain all the theories, and then after I will solve one example, which is really helpful for your examination purpose as well as for your career purpose. What is two-way slab? Two-way slab are the slab that are supported on four sides. This is a sketch of two-way slab in which at the end corner it will four column will be provided. So it is supported from all the four side. For a one-way slab, this is only supported two side as compared to two-way slab. So one-way slab which will be bend, this is two support, so bend, it will be bend like this from both side. But this in the case of two-way slab, it should not bend because at the all the side we will provided support. Second condition, ratio of longer span to shorter span is always less than 2. It is longer span Ly divided by Lx is always less than 2. This is Lx shorter span, Ly longer span. This is the advantage in a two-way slab. Deflection will be less and bending compared to one-way slab. That means deflection and bending will be less as compared to one-way slab. There are two conditions for the usage of a two-way simply supported slab. This is first and second condition. For support condition, as per IS Professor page number 90, simply supported slab, this is also called corners not held down. And then second condition, restrained slab, that means corners held down. What are the difference between simply supported and restrained? Let's clear. Corners are not fixed, so when load apply, end support or corner lifted up. That means this is the end corners which is not binding with the beam. So when the load apply over the mid span, the corner will be bent upward direction and torsion does not generate it. And the design as per IS Professor page number 90 clause number D2. I will show you in the IS code. This is the second case. Restrained slab is also called as corners held down, in which condition corners are fixed with beam. That means corner are binded with beam. When the load apply, corner does not lifting up. So this is the support which does not lifting up on the in the case of corners held down. So tension reinforcement is to be provided and designing as per IS Professor page number 90 clause number D1. You can see here IS Professor page number 19. This is the classification of two-way slab, and this is the middle strip, this is the edge strip for longer span, then this is for the shorter span. This distance is Ly by 8, this is Lx by 8. So these are this condition which I already told you. This is D 1.1 when the supported on four side with provisional for torsion and corner. This is same condition, corners held down and restrained. This is second condition, the simply supported on four side. You have to calculate alpha and alpha y. Alpha and alpha y is nothing but the ratio of Ly upon Lx. Ly means longer span divided shorter span. You can calculate the value of moment from using this equation. This is equation mx and my, in which ms is the moment on strip of unit width spanning along LX direction, and for my it will be along LY direction. Alpha x and alpha y is the coefficient given in isopress page number 27 and 26. LX and LY you already know. The criteria which already provided in alpha x and alpha y in the form, and for corners are held down. There are few conditions which I explain you in the next video. Today we are discussing about simply supported on four side. Also you can also call as a simply supported condition. Calculation of span by D ratio, we use always shorter span. The next is, and second is Lx is less than 3.5 meter and the loading class is less than 3 kN per meter square. And for mild steel, span to depth ratio, this is the two condition. If Lx is less than 3.5 and loading class is less than 3, we have to use multiply for the calculation of span by D ratio. Simply supported slab 35 and continuous 40. And 4, if Fe415, then multiply span by D ratio with 0.8. This condition given in IS Properties page number 39. For the two-way slabs, shortest span up to 3.5 meter width and loading class will be 3. We have to use simply supported 35 and continuous for 40. And for Fe415, we have to multiply this value by 0.8. This is the example and given data. The size of the slab is 3 meter cross 3 meter, supported width 300 mm. This is the live load 3 kN per meter square, floor finish 1 kN per meter square using M20 Fe415. And this is condition, corners are not held down. So step first, effective depth. What is the condition? We will check first of all condition, shorter span 3 meter, that means less than 3.5 meter. Okay. Second, live load 3 kN per meter square, which is less than or equal to 3 kN per meter square. Okay, so this is a kind of simply supported slab which already we told corners are not held down, so we have to use 35 page number which is 35. Assume 0.3% steel, and we have to calculate modified factor using IS 4/6 page number 30. This is 240 graph and this is 0.3% steel we assume. So almost here we will got the modified factor 1.5. This is the condition of simply supported slab which we are using 35. This is L by D 35. This is, and modified factor multiply 0.8 because this is the Fe415 steel. So we got the depth 71.42 mm and around we provided 110 mm. Small d is equal to 110 minus 10, it is 100 mm for longer side. We deduct depth diameter of the bar. Assume 10 mm clear cover, and capital D is equal to 110 plus, this is a 10 by 2 plus 20. 20 is the cover, and we got overall depth 135 mm. Step 2, calculate effective span. This is, we always calculate for the shorter span. First step, this first of all we will check IS Properties page number 32, clause number 20. This is the condition. The effective span of the member that is not built integrally with its support shall be taken as a clear span plus effective depth. That means clear span here 3 meter and effective depth we already got 110 mm. And the second is center to center of support, whichever is less. This is first condition is clear span 3000 plus effective depth. Second condition is center to center distance from this point to this point. That means clear span plus width divided by 2, and for this side width divided by 2. So this is a clear span 3000 plus 110, 3110, and second center to center support 3000 plus support total width divided by 2 and total width divided by 2. Then we require the value from smallest of the two, so we will get the Lx is equal to 3110 mm. We similar way Ly is equal to 3110 mm. Next step, load calculation. Here first of all we calculate dead load. Dead load means it is capital D into density. Capital D will be 135 mm. We will use 0.135 meter into 25. This is 3.375 kilonewton per meter square. Floor finish will be 1 kilonewton per meter square already given. Live load is same by 3 kilonewton per meter square. So we will summation of this 3 load, and after that this is the factor load 1.5 into 7.375. We will get 11.06 kilonewton per meter square. Next step, mid span moment. As per IS for physics page number 90 clause number D2, mx and my is equal to alpha x wlx square alpha y w lx. This is the equation of mx and my. We have to use only a length in x direction for the both condition, and this is the ly by lx table. Here our case ly by lx is equal to 1. So from table ly by lx is equal to 1, alpha x and alpha y 0.062. So mx and my both will be same because alpha x and alpha y which will be same. The equation is alpha x, that means 0.062 into w is the total load 11.06 into length in x direction, this is 3.11, which we are finding effective span. This is the 6.62 kilonewton into meter. Step 5, check effective depth through the flexor. This is the equation mu 0.138 FCK BD square. You can easily find out SP16 page number 10 table C. If you are putting, you can get the depth is equal to 49 mm. This is the required depth, and you provide 110 mm. So the slab which will be safe against flexor. So now we'll calculate the total reinforcement required for the along LX direction and for the along LY direction. First of all, we calculate along LX direction, and the depth will be 110 mm. So we'll calculate mu by BD square. This is we got, which we are using B 1000 for the unit weight. We got 0.54. Now we will calculate the PT. PT will be given in a using M20 Fe415 HP16 page number 40. Our PT value lies in between 0.50 and 0.54. This is 0.54. So our value in between 0.143 and 158. We have to calculate it using simple mesh solution, and we will got the value 0.54, near about 0.155. So we get PT will be 0.115. So here one condition, it support we bend up steel at 50% bend. That means we providing steel at the support like this. So this is the bent up bar. So at the support bent up will be 50%. So at the bottom of the support, that means for this part and the bottom like here, so, it will be less than 0.12. This means we have to provide 0.155% steel if we are providing 50% steel at bent up bar. So the value is near about 0.15, 0.07. we have to require minimum 0.12. So at a mid span we provide 0.24%. So at the support it will be 0.12%. So AST PTBD upon 100. Now we are using 0.24. 0.24 divided by 100. Width will be unit 1000 and total depth 135. This is the overall depth. We calculate 324 mm square. Provide 8 mm diameter at the rate 150 mm center to center. Along LY direction, this is the depth is 100 mm. So using mu by bd square, same way we calculate 0.63. PT will be 0.19 as per the SP16 page number 48. So we required minimum 0.24 percentage. The same way which AST will be 0.24, 1135 mm 100. We got 324 mm square. So we provide 8 mm diameter at the rate 150 mm center to center. Step number 7, check for cracking. This is the criteria which already mentioned in IS page number 46. We can watch first. This is the criteria for the slab. The horizontal distance between parallel reinforcement bar shall not be more than 3 times the effective depth, and the second is 300, whichever is smaller. And for distribution steel, this is shall not be more than 5 times effective depth, that means 5 times depth, and for PT whichever is smaller. This is given in IS 6 page number 46. This is and here our case both direction which will be main steel. So we have to check for the always for one. We have to always check for the main steel. So main steel criteria is a 3D and 300 mm. The 330, 300 mm, smallest is 3000. In our case, we got 8 mm diameter and 150 mm center to center, and the maximum allowance is 150 mm, which is less than 300 mm, so it's okay. For the along LY direction, same way we are using 3D and 300 mm. We got 300 mm, and the spacing for the LY direction is 150 mm. So 150 mm, which is less than 300 mm. So the slab is safe against cracking. Step 8, check for deflection. This is the allowable deflection, this is actual deflection. L by D is equal to, which we already provided equation 35, modified factor and 0.8. We have to calculate modified factor using the steel. So we get the modified factor 1.5. So L by D is equal to 35 into 1.5 into 0.8. We got 42. This is allowable deflection. Our actual deflection is length upon depth. Length will be 3110 divided by 110. So we get 28.27. You can also mention the unit, but this is also unit mm. Allowable deflection is 42 mm, 42, which is greater than actual deflection. So slab is safe against deflection. This is the last check for shear, in which we have to calculate maximum shear force is equal to Vu. Vu is W into Lx by 2. W is the factor load 11.06 and length in x direction is 3.11 divided by 2. We got 17.20 kilonewton. The equation is tau V is equal to Vu by Bd. Vu is 17.20. This is kilonewton. We have to record in Newton. So we will multiply with the 1000. And the effective width is 1000 mm and depth is 100 mm. So we will get 0.172 megapascal. You can also say Newton per mm square. So tau we will get. So now for the tau C part, we have to calculate PT. PT is 100 AST upon BD. This is the maximum area of steel which we are providing. 100 into 335 divided by with 1000 and depth will be 100. we got 0.335%. For the calculation of design shear strength of concrete, we have to calculate at 0.335. So we have to calculate in between 0.25 and 0.50 using m20, 0.36 and 0.58. Our answer lies in between this. 0.25 we get 0.36 and 0.5 we get 0.48. So the at the 0.335 we get the answer 0.398. This is the tau c dash is equal to k into tau. This is the design shear strength of the concrete equation, tau c into ks, tau c which we already calculate, and the value of k depending on the depth of the slab. Our depth of the slab is 135 mm, so we have to use the k value is 1.3. This is 1.3 and tau c 0.398. So we got tau c dash is equal to 0.517 Newton per mm square, or you can say megapascal. So the tau c dash is equal to 0.51 square Newton per mm square, which is greater than tau v. So design shear strength of the concrete which is greater than nominal shear stress. So the slab designing is safe against shear. This is the reinforcement details. This is start from this portion and it will be go like this, and this is start from this point and it will go like this. This is x direction steel, and this is the y direction steel. You can see here this steel like this, and this steel start from here and continue till here. In the same way this steel bend like this. This is 80 mm diameter at the 150 mm center to center along LX. You can see along LX we provide 80 mm diameter at the 150 mm center to center, and this is along LY direction. This is LY direction. So we provide 80 mm diameter at the 150 mm center to center. This is also you can see along LY 80 mm diameter at the 150 mm center to center. I will explain this sketch again. This is the bend length 0.1 into length from this point to this point. This is 310 mm. This is overall depth, and this is effective depth from the center of the main bar. This is the clear span 3000 mm, and this is the this is the effective span. LX is 3110 mm. This is the second sketch. This is a weight support. This is a weight support. This is clear span from y direction, and this is 0.1 times length. This is this steel like same way here, bend here, and next will be start from here, and it will be go through this direction. And for this for LY direction it will start from like this, and the next bar, this is next bar, this is like this. This is the 80 mm diameter at the rate 150 mm center to center along LY direction, and this is along LX direction. This is the plan view, and we cut the x section, and you already know, I already told you about this section. So thank you for the watching video. Like this video, subscribe my channel and share with your friends. Thank you. Have a good day.